Good morning, students. Welcome to Bindu Dhadwal chemistry lessons. Today we'll be doing general characteristics of compounds of the alkaline earth metals. The dipositive oxidation state M2 positive is the predominant valence of group 2 elements. The alkaline earth metal compounds are predominantly ionic, but they are less ionic than compounds of alkali metals. This is due to increased nuclear charge and smaller size. The oxides and other compounds of beryllium and magnesium are more covalent in nature, but the oxides and other compounds of calcium, strontium, barium, and ionic compounds. The general characteristics of some of the compounds of alkali earth metals are as below: oxides and hydroxides. Now, the alkaline earth metals burn in oxygen to form the monooxide, which, except for beryllium oxide, have a rock salt structure. Beryllium oxide is covalent in nature. The enthalpies of formation of these oxides are quite high, and consequently they are very stable to heat. The beryllium oxide is amphoteric, but oxides of other elements are ionic in nature and basic. They react with water to form sparingly soluble hydroxide. So metal oxide plus water will form metal hydroxide. The solubility, thermal stability, and the basic character increases with increase in atomic number from magnesium hydroxide to barium hydroxide. The alkaline earth metal hydroxides are less basic and less stable than alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acid and alkali both. So with base it's going to form berylate ion, and it will also react with acids. Halides of alkaline earth metals. So halides of beryllium are essentially covalent and soluble in organic solvents, but of other members are ionic in nature. Beryllium chloride has a chain structure in the solid state where each beryllium is tetrahedrally attached to 4 chloride ions, 2 by covalent bonds and 2 by coordinate bonds. In the vapor phase, beryllium chloride tends to form a chloro-bridged dimer. So 2 BeCl2 molecules will combine to form a dimer in the vapor state. At a temperature of 1200 Kelvin, it will further break into a monomer which is linear in shape. The tendency to form halide hydrates gradually decreases down the group. Magnesium chloride has 8 water molecules attached to it. Calcium chloride dot 6H2O, strontium chloride 6H2O, barium chloride 2H2O. So hydrates, the tendency to form halide hydrates decreases down the group. The dehydration of hydrated chlorides, bromides and iodides of calcium, strontium and barium can be achieved on heating, whereas for magnesium and beryllium, the hydrated halides will suffer hydrolysis on heating. That is, water will break down and get added to beryllium and chlorine to form hydroxide and hydrogen chloride. The fluorides are relatively less soluble than chlorides owing to their high lattice enthalpies. Salts of oxoacids. Carbonates of alkaline earth metals are insoluble in water and can be precipitated by addition of sodium or ammonium carbonate solution to a soluble salt of these metals. The solubility of carbonate decreases as the atomic number increases. All carbonates decompose on heating to give carbon dioxide and oxide. Beryllium carbonate is unstable and can be kept only in atmosphere of carbon dioxide. The thermal stability increases with increasing cationic size. Sulfate. All sulfates of all alkaline earth metals are white solids and are stable to heat. Sulfates of beryllium and magnesium are readily soluble in water. Greater hydration enthalpies of beryllium and magnesium ions overcome lattice enthalpy factors, and therefore their sulfates are soluble in water. The sulfates of other alkaline earth metals, from calcium to radium, the solubility will decrease from calcium sulfate to barium sulfate. Nitrates are made up by dissolution of the carbonates in dilute nitric acid. Magnesium nitrate is crystalline with 6 molecules of water, MgNO3.6H2O. Barium nitrate crystallizes as the anhydrous salts. So this shows that down the group there is a decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. All decompose on heating. Nitrate will decompose to give metal oxides along with nitrogen dioxide and oxygen, behavior similar to that of lithium nitrate. The metal shown here can be beryllium, magnesium, calcium, strontium or barium. It's interesting to see that the solubility of alkaline earth metal hydroxide increases down the group, whereas that of alkaline earth metal carbonate and sulfate decreases down the group. The different behavior is, in case of hydroxides, the anion being common, the cationic radius will influence the lattice enthalpy. Although both lattice enthalpy and hydration enthalpy decrease down the group, but lattice enthalpy decreases much more than the hydration enthalpy. So as a result, in the end, the hydration enthalpy being greater than the lattice enthalpy causes it to be soluble. So solubility increases down the group. With increasing ionic size, solubility increases down the group. In case of alkaline earth metal carbonates and sulfates, solubility decreases down the group because size of anions is much larger than cation. So lattice enthalpy remains almost constant within a particular group, and hydration enthalpy decreases. So the solubility decreases down the group. Anomalous behavior of beryllium. Beryllium shows properties different than the rest of the members of the group. It shows anomalous behavior as compared to magnesium and rest of the group. It is because of exceptionally small atomic and ionic sizes of beryllium and its ions and high ionization enthalpy. And it forms compounds which are largely covalent and get easily hydrolyzed. Beryllium does not exhibit coordination number more than 4, as in its valence shell there are only 4 orbitals, no d orbitals, whereas remaining members of the group, all these, can have a coordination number of 6 by making use of its d orbitals. The oxides and hydroxides of beryllium are amphoteric in nature. The oxides and hydroxides of other members are basic in nature. So this explains the anomalous behavior of beryllium. Beryllium also shows properties similar to the element placed diagonally across it in the next group, the second element which is placed diagonally to beryllium. This relationship is called diagonal relationship. The ionic size of beryllium ion is estimated as 31 picometer, and charge to radius ratio is nearly same as that of aluminium ion. Hence, it resembles aluminium in some ways. For example, like aluminium, beryllium is not attacked by acids because in both the cases there is a presence of oxide film on the surface of metal which does not allow acids to attack them. Beryllium hydroxide dissolves in excess alkali to give a berylate ion, just as aluminium hydroxide gives aluminate ion. The chlorides of both beryllium and aluminium have Cl negative bridged chloride structure in vapor phase. Both chlorides are soluble in organic solvents and are strong Lewis acids, and they are also used as Friedel-Crafts catalysts. Beryllium and aluminium ions have strong tendency to form complexes, so these are their similar properties. Next is, let us study some important compounds of calcium. First is calcium oxide. It is also known as quicklime. The formula is CaO. Its uses, it's an important primary material for manufacturing cement and is cheapest form of alkali. Calcium oxide is used in the manufacture of sodium carbonate from caustic soda, NaOH. It is employed in the purification of sugar and in the manufacture of dyestuffs. Calcium hydroxide is also called slag lime and its formula is CaOH twice. It's used in the preparation of mortar, a building material. When you attach bricks, the ingredient that you place in between them in order to attach them is called mortar. Calcium hydroxide is used for its synthesis. It's used in whitewash due to its disinfectant nature, and it is used in glass making. It is used in tanning industry, also used for preparation of bleaching powder and for purification of sugar. Calcium carbonate, also known as limestone, has the formula CaCO3. It's used as a building material in the form of marble and in the manufacture of quicklime, CaO. Calcium carbonate along with magnesium carbonate is used as flux in the extraction of metals such as iron. Specially precipitated calcium carbonate is extensively used in the manufacture of high quality paper. It is also used as an antacid to reduce acidity. It's used as a mild abrasive in toothpaste, a constituent of chewing gum, and a filler in cosmetics. Next compound is calcium sulfate hemihydrate, which is better known as plaster of Paris. The formula is CaSO4 half H2. The largest use of plaster of Paris is in building industry as well as plasters. It's used for immobilizing the affected part of organ where there is a bone fracture or a sprain. Plaster is set on the broken part. It sets into a solid mass, does not allow the organ to move, and gives it time to heal, and the bone can be repaired. It's also employed in the dentistry, in ornamental work, and for making casts of statues and busts. That's all in today's video. This brings us also to the end of the chapter. If you like the video, please do share and subscribe. Thank you. Have a nice day.